Hello dear students. So as you know we have been continuing error propagation and so far we have studied how error propagates in addition, subtraction, multiplication and division. Today we will do the last part, that is error propagation in measured quantity raised to a power. So as you can see we have taken an example, x is equal to a raised to power n divided by b raised to power m. Considering the equation in proper error limits, we can rewrite it as x is equal to a raised to power n into b raised to power minus m, and then taking logarithm both side, log x is equal to n log a minus m log b. In this equation I would like to tell my students who have not studied in mathematics too far how to use logarithm. The power of a logarithm comes ahead in multiplication, and if the variables are in multiply, then it becomes addition in the logarithm. So you can understand in both ways, a raised to power n divided by b raised to power m. You can consider if it is in division, the logarithm will become minus, or you can write it like multiplied by b raised to power minus m, so minus n will come ahead. I can again separately discuss this thing with you in Zoom application session, or if you are having any doubt you can ask to me in person. Then differentiating this equation both side, for log x it will become dx by x is equal to n dA by a minus m dB by b. This is also a formula which you will remember, that for log x it is 1 by x, and similarly for log a it is 1 by a, and log b it is 1 by b. Differentiating both side we get this equation, and the next step is very important. We can write the dx, dA and dB terms of differentiation in terms of errors, that is delta x, delta a and delta b. So delta x by x becomes plus minus n times delta a by a plus m times delta b by b. So you can here see that error in the quantity raised to a power, suppose here it is n and m times, so the error is multiplied by the power. That is how error propagates in power. So whatever is the power, error becomes multiplied by the power. This formula can be continued for more than two quantities. Next point is accuracy and precision. Accuracy and precision are quite similar to each other. The accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity, while precision tells us to what resolution or limit the quantity is measured by a measuring instrument. An example explaining accuracy versus precision is here. You can see three diagrams are here. First of all, let us consider diagram A. In diagram A, you see that there is a target on which bullets are fired, and bullets are fired such that they are neither close to each other and neither they are close to target. So you can say this target on which bullet is fired is neither accurate and nor precise. Now look at the target B. You can see all the bullets are close to each other, but they are not close to the target. This is the target. So you can say this calculation is precise but not accurate. So this is an example of precise shooting. And then in the third example you can see all the bullets are close to each other and also close to the target. So this is precise as well as accurate. So this is the difference between precision and accuracy. Comparison, and also you can say how do we understand precision and accuracy. So next is common rules for counting significant figures. So for significant figures I would like to guide you all students that you must go through all the rules carefully which are provided in your textbook. I will give you a fast reading of these rules. Like in given any figure, all non-zero digits are significant. Second, all zeros occurring between two non-zero digits are significant no matter where the decimal point is. For example, 1007 has four significant figures. The zeros in between are also significant. Rule number 3, if the number is less than 1, then zeros on the right of decimal point and to the left of first non-zero digit are not significant. तो इसका एग्जांपल है 0.005704. इन दिस टू zeros after first decimal point are not significant as to the left of decimal point there is 0. Conversely, if on the left there would have been a non-zero digits, then these two zeros would have been significant figures. Rule 4. A number without a decimal point, the terminal or trailing zeros are not significant. So in 3210, only 321 is significant. However, in a number with decimal point, trailing zeros are significant. For example, 3.500 has 4 significant figures, while 0.0069000 has 5 significant figures. So these are the 5 significant figures which I underlined with red, and these 3 zeros are not significant. Change of unit does not change the number of significant figures in the measurements. Digit 0 conventionally put on the left of a decimal for a number less than 1 is never significant. So 0.3570 has 4 significant figures. This 0 before point is not significant. Multiplying or dividing factors which are neither rounded numbers nor numbers representing measured values are exact have infinite number of significant figure, and we can take them up to the decimal point as much accuracy we want. Like 2.0, 2.00, 2.000 have 2, 3 and 4 significant figures, or there can be more. Similarly, the rule for trailing zeros can create the confusion. So here the thumb rule is, if the number of trailing zeros are result from a calculation, then they become significant, and if they are not from a calculation, then they are not significant. Practice this on few figures for finding out number of significant figures, and you will get through it. It needs a little practice to calculate exact number of significant figures. And the second point is rounding off. Rounding off is something which you have been doing in previous classes too, but I'll give you an example in brief, that the digit to be dropped, like for example 3.94, and you can see 4 is less than 5, so we will not change 9, so it will remain 3.9. On the other hand, you can see as it is 7.82, as 2 is less than 5, so 8 is not changed and it is rounded off to 7.8. On the second hand, if the trailing digit is greater than 5, like in this example 6.87, 7 is greater than 5, so this 8 is increased by 1 and we rounded off to 6.9, and 12.78 is rounded off to 12.8. If the digit to be dropped is 5, because these two cases we have discussed for less than 5 and greater than 5, but if it is equal to 5, then what we'll do, then we'll observe the digit following 3. If it is odd, we will increase it by 1, as in this example 16.351 is 16.4 because 3 is odd, and if it is even, then we will not change it, like 3.205 3.250 rounded off is 3.2, as 2 is even and the number is 5, so we have not changed it. If the digit to be dropped is 5 or 5 followed by zeros, then preceding digit is raised by 1 if it is odd and remains unchanged if it is even. And in arithmetic operations with significant figure, when we are doing, there is a thumb rule, when we are doing addition, subtraction or multiplication or division, we always express the result in such that it must have significant figures equal to the least significant figures available in the calculation. So for example, 3.8 and 0.125, and we need to multiply them, the 0.475 is the answer, as least number of significant figures is 2 in 3.8, therefore result must also be rounded off to two significant figures, that is 0.48. Again, another example, when mass given is 4.237 gram and volume is 2.51, then we know that least significant figures are 3, so result is to be expressed in 3 significant figures, that is 1.69. so this long result is rounded off to 1.69. and same rule we apply in addition and subtraction. Result must be expressed in equal to number of significant figures which are least in any of the operand involved. Thank you. See you in next lecture.